Now, the biggest challenge really this time is to find where the beauty really is. Now, obviously, if you look at the properties, there are several properties which are really very easy to see. For instance, we see that this group is closed. Why? Because if I look at the elements here in the Cayley table, I see that it only uses the elements of Z7 except the 0. You see also the symmetry. You see, for instance, 2, 2, 3, 3, and so on. So it's symmetric around this diagonal. So this group is Abelian because the commutative law applies, right? You can also prove that if I have two cyclic groups, that if I have two groups, and they are isomorphic, then G is cyclic only if H is cyclic. So it is a property which is transferred through the idea of isomorphism. These are really not that impressive properties. The real beauty really is hidden down deep, and so let's have a look at that. And again, I look at this Cayley table here. Let's explore this table a little bit further. For instance, I have here this row, column, sorry, and this row, and I'm going to swap this row and the row of the column of 2, and the row of 2 I swap with the column of 3, and the same I do, and the column of 6 goes over there, and the row of 6 goes over there, and then my table will look like this. This table I already swapped the columns, and now I'm going to swap the rows. I did now, and all of a sudden you see this beautiful structure emerging. You have not only the symmetry in along the main axis diagonal here, but you have also 1, and then you have 3, and then you have 2, 2, 2, and you have 6, 6, 6, and so on, 4, 4, 4, etc., etc. Now, but this is not all, because if we take this a little bit further, and we assume that I introduce now a variable a, and I choose a being 3. Okay. In that case, a squared would be 3 times 3 modulo 7 gives me 2. You see, 3, 3, 2, 2. A to the power 3 was 6. 6, 6. A to the power 4, was that 4? Yes, indeed, it was 4. You see this 4. And a to the power 5 being, yes, indeed, 5. So all of a sudden we have here this row, quite unexpectedly. Here we have a to the power 0, a to the power 1, a to the power 2, a to the power 3, a to the power 4, and a to the power 5, and of course here the same. Okay, and not only that, but if I am going to replace these elements of the Cayley table with the powers of A, the table turns into this. You see all of a sudden here the inherent beauty of this structure, quite unexpectedly. But you see here A's, the A to the power 2, and so on and so on. Now, this is what I like about math. You have these hidden structures with their own beauty, so to speak, if you see it. Now, the logical question would now be, we took now Z7 except the 0, so we had a group of the order of 6. Now, would this also work with different orders? And in fact, the answer is yes. Now, the theorem is that if I have a group of the order n, that there is always at least one group that is cyclic. So first of all, we need to make a group of order n which is cyclic, and then indeed prove it that it is a group. So I take G, and for G I take A to the power 2, A to the power 3, and so until A to the power n, where A is one of the generators. That's why it's called a generator. Now, obviously, A to the power n equals E, like for instance the generator we had 3 was 3 to the power 6 being the order of the group, was indeed the identity we had back then. So this is always true. So in case n equals 1, then G has only one element. That then by definition will be the identity. If n equals 2, then G will have two elements, where A squared will be the identity, and so on and so forth. So what I have here at least is cyclic, and the question is now, is it a group, yes or no? Now, in order to prove that, we need to show that it is closed, that it is associative, that it has an identity, and that it is inverse, or it has an inverse operation. And I start with the first one. Now, when I look at the closure or not, I take two elements of G, A to the power P and A to the power Q, where both are between 1 and n, since they are an element of G. Now, I apply the star operator, and of course then this will be A to the power P plus Q, and the question is then, of course, will this be an element of G again, because it needs to be closed? That's the question. Now, there are two possibilities. Possibility 1 is that the sum of P and Q is somewhere between 1, or actually 2, because both of them has a minimum value of 1, and n. In that case, obviously A to the power P plus Q will be an element of G. Now, in the second situation, where P plus Q exceed n, for instance, both are n, so the sum will be 2n, they are somewhere between n and 2n. So we could be able to write that they are n plus some remainder r. R then being between 1 and n. Okay, now if that would be the case, then it looks like this. P a to the power p plus q will then be e to the power n plus r, or it will be a to the power n star operation a to the power r, and since this a to the power n equals e, it will be a to the power r. And because r is somewhere between 1 and n, I can conclude that a to the power r indeed is again an element of G, and therefore it is closed. Now the associative characteristic is really very simple. We take three elements and we apply the star operator, and I first look at the situation where I'll operate first a to the power q times a to the power r, which gives me then a to the power p star operator a to the power q plus r, which in the end gives me then a to the power p plus q plus r. In the other, this is a p situation where I first apply the star operation between a to the power p and a to the power q, I have of course this, and this gives me of course the same result, so therefore it is associative. Well, the identity already was taken care of because I knew a to the power n was e. Now the last characteristic we need to prove would be the characteristic of that there needs to be an inverse operator. Now to prove that, I take two elements of G, a to the power p and a to the power q, and they need to be each other inverse operators. So I apply the star operator, and somewhere there needs to be the result e. Now this would be true if p plus q would be n, because of course the star operator gives me a to the power p plus q. So if I could do something with this idea, then I would know that the result would be the identity, and then I've proven what I wanted to prove. Now the question is, of course, can I find a situation like this in every circumstance? Well, if p plus q equals n, then obviously q equals n minus p, where p is somewhere between 1 and n, so n minus p should be somewhere between 0 if p equals n, and n minus 1 in the case that p equals 1. So therefore q should be something between 0 and n minus 1. Now, is that possible? Well, I look at two situations. The first situation is when q equals 0. Well, in that case it's easy. Then p equals n, and these are each other's inverse operators. In the case that q is not 0, q is somewhere between 1 and n minus 1, so obviously a to the power q is an element of G. So therefore I know that under every circumstance, if I have an element a to the power p, I can always find another element a to the power q, which gives me the result that this is true, and so therefore I prove this inverse characteristic.